Part 2, code quality. Let's look at the current state of how we teach programming and code quality. Here's the first thing we teach you. We teach you how to take an empty document and create code version A using a couple of patterns of well, this is how you do things, this is what you're supposed to make. Here's a text editor, go have fun, try stuff. And then on the other end we teach you how to compare. Let's look at two versions of code, and we are teaching you to be in agreement that version B is better than version A for some version of B and some version of A. So we're teaching you not just to look at multiple pieces of code, but to compare them and to form a consensus on what is better. And then you get the exam, and the question is improve. Here's a version of code A, and you are supposed to improve it. Which means that you need to understand the comparing part, but you also need to understand the creating part, but we don't really teach improving as a thing. We don't really give you exercises on that part. We just demand that you're able to combine these two pieces of information and say, this is the way you do it. So we tend to teach creating and comparing independently and not really combine them, and we definitely don't really teach improving a piece of code, unfortunately. So my goal is one of unification of these two. In part one of this little mini-series, I talked about the design patterns that emerge from the constraints of the problem and the constraints of what I claim to be code quality, or what I claim to be good code quality. And the goal was to give you some practical tools that are solid defaults. They're not applicable in every scenario, but they're good places to start. So here's a short recap. State machines, the core and shell, the separation by modification, the reference-free communication with channels instead of references to other objects, and distributed systems. These are all practical tools that you can use, and probably should use as well. And then in part 2, I want to look at it from the other perspective. I want to give you the understanding of code quality that lets you create new patterns, or lets you apply these patterns or different patterns to new and novel contexts. Not just how do we compare two pieces of code and say which one is better, but actually know and understand code quality deeply enough that you are able to use it when creating code, not just when comparing code. It has to be done. Why do we care about code quality? Every time somebody talks about it, this slide has to be there. There's no escape. I start with something controversial, of course. If it works, if our code works, what does it matter what it looks like? Why do we care? Well, the reality is that most code doesn't work. At least most of the time we spend with our eyeballs on a piece of code, it is in a non-functioning state. We don't spend a lot of time looking at code that is working, because why would you? It's working. There's nothing to do here. It's only the broken stuff that's worth looking at. So how do we care about code? What are these mechanisms? What are these tools of thinking that we are using? Well, here's one extreme. We use these checklists, and we just say if it satisfies 176 of 243 criteria, it's better than the one that satisfies 138. Pretty objective. Everybody agrees, of course. And then on the other extreme, we just say, well, this one feels better. Or I have faith that this one will be easier to work with in the future. And there's nothing objective about it. We're just kind of winging it. Now my goal is actually to move you towards this feel direction and away from the checklists. Because what is the point of these checklists if we don't understand what quality even means? Like, sure, we can follow this checklist and we can argue from these checklists, but quality, what, why, how? The thing is, these checklists don't help you when creating new code. It's like, oh, does this function that I haven't made have this number of parameters? I don't know, I haven't made the function yet. It doesn't work. Let's look at some examples from checklists. These are from Code Complete. There are also from other chapters that we haven't given you, just to give you a broader look at Code Complete. Try to think about, how would I use this when writing new code? From a blank text editor, how would I use these checklist rules? If a routine has a decision count more than 10, is there a good reason for not redesigning it? I don't have a routine yet. I have no idea what the decision count will be. Besides, what is a good reason for redesigning it? What do we mean by good reason? Have relatively independent groups of statements been moved into their own routines? Don't have any routines, don't have any statements. What is relatively independent? And in the first place, why exactly do we make routines? From a code quality perspective, why do we even do this? Are cases ordered meaningfully? This is from like a switch case. Are the cases in a switch ordered meaningfully? Okay, danger of getting too philosophical, but what really is meaning in this context? And what makes an ordering meaningful? Have you even thought about this? Chances are probably not. Is the length of a routine determined naturally by its function and logic, rather by an artificial coding standard? Okay, what is natural? And how do we find this length in a natural fashion? And then, of course, one of my more favorite rules, does the routine have 7 or fewer parameters? And of course the question is, why is there an artificial coding standard? And then this is a chapter which you haven't touched on, which is having a quality assurance plan. So, in your quality assurance plan, is the quality measured in some way that you can tell whether it is improving or degrading? Well, the checklist for the chapter contains a question which is, have you done something? Again, not super useful. And then my absolutely favorite rule of all of them from the naming chapter, are the names pronunciable? Of course, everything is pronunciable if you are brave enough. Right, so I have a couple of problems with checklists, let's be honest here. How do we interpret the rules? There looks like there's some room for interpretation here. If there are ways of interpreting, maybe there are consistent ways of interpreting, so maybe there are rules for applying the rules. Maybe there's one rule for each rule, or hopefully there's one rule for all of the rules. That rule for how to apply the rules, that one singular rule, that's what I'm looking for. Then how do we decide if this is a good checklist? How do we decide if each point is relevant? How do we decide which points are more valuable than others? If we satisfy 138 important points, is that better than satisfying 176 bad points? And where do these rules come from? Somebody sat down and made these rules. How were they thinking? What was their vision? And maybe if we can get into the mind of the people who make these rules, maybe we can grasp at some understanding that they have. So let's see if we can find this understanding. And then I have the problems of the application. How do we apply these kinds of rules for writing code from scratch? Chances are there aren't any checklists that lets you write code from scratch. If there was an algorithm for the act of programming, why would we teach you how to program? We already have a computer that can just satisfy the algorithm. So of course, there are no checklists for making code. Why would there be checklists for checking the code quality of code that hasn't been written yet? It doesn't make a whole lot of sense. So in the end, let's see. Is it possible for us to skip right past the checklists into some more deep and substantial understanding of code quality? Spoilers, yes. And can we find an understanding so substantial that we could write these checklists from scratch ourselves. That way we won't have to remember them or look them up. So that's good. Before I give you what I think is my understanding of code quality, I want to give you the tools for you to both follow me in the way I think, and also to give you the tools to think about this problem yourself. Chances are you already have these tools, but it's worth going through again just to get a nice little refresher of the ultra basics of philosophy. So these are the approaches that I will be taking to find this understanding of what quality even means. The first way to look at it is to look for patterns in what we believe is good code. Looking for patterns is descriptive. We're trying to describe the property of good code, and we're also trying to describe our intuition for what good code is. Look, we're trying to make a four-way matrix here. We can also look for patterns, or we can look, oh Jesus Christ, these are in a completely different order than what I was expecting them to be, even though I made them. This is interesting. Looks like we're going clockwise, people. All right, we can look at what makes a good rule. What makes a good code quality rule? So this is, instead of top-down describing the properties of code, we're going bottom-up and prescribing what kinds of rules would it follow if it were to become good code. No, we're not going clockwise anyway. There's the other way of thinking about it. Instead of looking for patterns in the code, we're looking for patterns in the rules and seeing if we can find patterns in the rule set. In this case, we're not looking for our intuition. We're not using our intuition. We're not using our faith in our property of goodness. We're trying to reduce analytically and logically what these rules mean, which gives us one corner left. Hopefully, it is now obvious which one will show up, and hopefully this presentation also follows this pattern. Yes, it does. Good. At least something remains. We can also see if we can find some logic in rule sets. So hopefully, if the rules follow some logic, if the rules follow some pattern, they will construct a valid set of rules for code quality. Now these four, hopefully, if we have a good understanding, these four will be unified into a single whole. So let's look at what the problem is. Here's my problem. We hope that the existing code quality rules will guide us into making good code. And we also hope that if we have written good code, if we have written what we deem to be good code based on our intuition, it happens to follow the rules that somebody else has written. Now, given that I just took a wild dump over the checklists, this is a gap that needs to be bridged. We cannot take this for granted. At least I did not take this for granted. So, we have this gap here. Let's try going the other way. Let's compare these two instead. The patterns in good code, or good in code and good in rules. When we make code we think is good, we expect it to follow some rule. We don't know what that rule is, but we expect there to be some rule for this. There is a pattern for goodness. And if we follow the rules that we think are good, we expect it to produce code that we think is good. Let's look at if these two connect. We believe that logical rules are good, as in logic has the moral quality of being good. We have faith in logic. I mean that seriously. And this isn't some postmodern bullshit. We have faith that logic and math and patterns and classifications and all of these things will guide us to a better world. Seriously. We believe this. Otherwise, why would we use logic? If we didn't believe this, just throw logic and math and all that stuff out the window, it doesn't matter. But we believe that it works, so we keep using it. And we also believe that the things that make rules good is the property of possessing this logic. If we analyze existing rules, we expect there to be some logic behind them. We expect that whoever made the rules didn't just write random shit, but actually thought about it. And if we go the other way, if we have some understanding of what makes a set of rules a good set of rules, not just an individual rule, but a property for the set of rules, we expect that the code quality rules follows this set-wise logic. So if we go this other way around, we should be able to bridge the gap between our understanding of the rules for code quality and the properties what makes the code good. So this is our two-sided problem that we need to solve. We need to analyze these rules to see if there is a logic to them. And we need to establish the principles for what makes a set of rules a good set of rules. And then we need to see if our rules, the code quality rules, follow them, or if there is some hidden understanding underneath there that lets us interpret them in a way that makes them follow the principles for good rules. Now it's a two-sided problem, which means we can start in both ends, right? So if we start by analyzing the rule sets to see what logic lies within, we need to understand what is the premise for analysis, what makes analysis valid. So here's our little philosophy part. So we need to rules for what constitutes valid analysis. Great. More rules. How do we deal with this? We just have rules upon rules. Here's my hypothesis that should make this a bit simpler. The way we think about code quality is the same as the way we think about code quality rules. What do I mean? Both ways of thinking are concerned with this way of good thinking. Consistency, logic, structure, and so on. The metric by which we say that the rule set is good is the same metric as we use for saying if the code is good. We're looking for consistency in the rule set, we're looking for consistency in the code. We're looking for logic in the rule set, we're looking for logic in the code. We're looking for structured properties in the rule sets, we're looking for structured properties in the code. That's my hypothesis. So that lets us get away with analyzing, well, we can now start analyzing in both ends at the same time, hopefully, and we can analyze it based on our intuition for what constitutes good analysis based on what we've done before. So we don't need rules for valid analysis, we can get away with intuition for valid analysis. Our intuition is consistency, logic, structure, and so on. So let's look at some basic tools of analysis. These are things that you have hopefully encountered before, either directly or indirectly through high school and university. Here are the 4 levels of, well, there are actually 4 levels of essay writing, but if you know how to write and you know how to formulate an argument, you also know how to think. So this is at least what I did in high school, in English class. It's just worth having a brief recap on it. Here's the lowest level. You have a text, and we form a description of that text. It's just a basic retelling. It's just saying the thing that the text says in your own words. It doesn't really demonstrate any understanding. That's the lowest level. 1 level up, we have a commentary. we're now not just retelling everything, but we're highlighting the things that are significant. We're picking out the things that matter most, which requires some amount of perception of what importance means. And since we're able to identify important things, that means we're demonstrating at least some amount of understanding. One level up, we can get to a discussion. And in our discussion, we're not just highlighting things, but we're actually looking at a sequence of multiple things that share importance. But we're just looking at one thing. And at the top is analysis. Analysis is discussion, and it also is commentary, and it also requires description. But the thing that makes analysis is linking not just a very small focused part, but linking across a wide range of things. Making these links across aspects, across themes, across ideas, and finding an ordering between them, and finding a logic within them, that is analysis. That is a level that we need to be at to understand this. Here are some tools of analysis, which again, you've encountered before. The classic one being comparison. We're looking for similarities, we're looking for differences. Looking for differences only really makes sense if there are some amount of similarities. So a classic exam question would be, compare the economic preconditions for World War I and World War II. That's a typical history exam question. What is not a typical history exam question is compare World War II and this cow. Because there is no reasonable connection to be made between them. Differences require similarity to make sense. Another analytical thinking tool is a more experience-based one. We try to shift our perspective. We try to look at if there is a connection between two things over here, there's a connection between a similar set of two things over there. We're trying to look at the same thing but in different contexts. An example of this would be the trolley problem, which chances are you're already familiar with. You have one person lying on the tracks over here and 5 people lying on the tracks over there, and the train's going to run over the 5 people unless you actively intervene to make it run over the one person. And the question is, what is the morally correct thing to do? And then the variant of this is, well, that one person is someone special, or the 5 people are zombies and they don't really matter, for examples. And just changing the context of the problem lets us analyze the problem from different perspectives to reach slightly different but hopefully the same conclusion. And in order to do this, in order to see the world from a different perspective, that requires experience. So it's not just pure analysis, it requires time. And the final one, which since you're in the realm of science you should absolutely be familiar with, is the concept of experimentation. You're looking for counterexamples, counter-arguments, to see if your hypothesis is correct or if it is immediately dumpstered by some counterexample. You're always trying to disprove. And the example for this is just testing in general. You have some pattern, you're looking for counterexamples to see if you find something that doesn't fit the pattern. So with these tools and this way of thinking, let's see if we can find it. Can we find a singular quality, some kind of quality, which is valid across the widest possible range of software artifacts? So independent of programming language, independent of what kind of project it is, independent of what the requirements are. It is valid at all levels of resolution within that project. So we're cross-referencing the size of a file, the size of a module, the size of a function, the size of a single line, the size of the name of a single variable. The same rules should apply to everything. The same concept of quality should apply to everything. And we want it to be quantifiable, so that we're not stuck with a bunch of engineers who don't agree what quality means. And we want to be able to measure it in some either objective or at least intuitive way to resolve disagreement, so we're not stuck in situations where everybody thinks it's subjective. And we also want it to be qualifiable, to resonate with the intuition of the programmers that are making this software. So let's look at the code quality rules that we've been given. And now, of course, exercise for the reader before we continue. And for the majority of you who are watching this video, I suggest you take a break now to look at the code quality rules and see if you can find some patterns within them. See if you can identify this metric. See if you can identify what this quality is. Here's what I found. The rules are about things, and the rules are concerned with things. So let's first split them on the about dimension. They're about the individual components, like variables, statements, routines, and control flow. And they're about how to compose these components into objects, modules, interactions in general. And they're concerned with how we use these and how we compose these. So they're concerned with the scope, the size, the visibility of these variables, statements, routines, the assumptions we make in order to construct these modules, interactions, routines. They're concerned with the meaning of variables. What does it mean? What does it do? What is the purpose of creating this object? What is the purpose of having this interaction? And they're concerned largely with interaction. Cohesion, coupling, grouping, nesting, where we put things, both visually and conceptually, and how we connect them. So, what is the principle that underlies these rules? And what is this quality that the rules want to enforce? Well, there are things that are concerned with boundaries. There are boundaries between objects, the boundaries between what goes in an object and what goes outside an object, as well as modules and functions. There are how we connect these things, how we connect objects, how they talk to each other, how we group functions together, how we group things thematically. There are these relations between how these names should interact, how things that have the same usage pattern should be in the same place, and things that are concerned with the same idea should be in the same place. We're starting to see a pattern here in the betweeniness. Between seems to be a word that is repeated here. And then we have this one, the limits. Limits in size, no more than a certain number of parameters, for example. And the limits in nesting, no more than 10 conditionals. Now we have this nice betweeniness here. Is it possible to formulate this one as a between as well? This one might be hard to see, but I've slightly covered it before. This one is between potential. We're limiting the scope of a variable because if we don't, it can potentially be used somewhere else. Reducing the scope limits the amount of potential abuse of something. Limiting the nesting, every level of nesting interacts with every other level of nesting. The deeper we are in this hierarchy, the more context is required to understand the inmost part. And the outermost part, for it to work, relies on these innermost parts. There's an interaction between each level of nesting, and there is an interaction between each else in an if. This interaction is the thing that we want to limit. That's why we limit the amount of nesting and the size of our conditionals. So we can formulate this one as a between as well. So between seems to be a recurring theme. Let's see if we can find a word for this. Here's the word for this. Complexity. What does complex mean? Well, it's made of two subcomponents, of course, together and woven. So complex means things that have been woven together. You can think of it as intertwined, braided, and so on. Oppose this to compose, which is to place together. They're just next to each other, but they're not interacting with each other other than by proximity. We can also compare it to simple, which means one-fold, plain, or duplex, which you've also encountered before, which means twofold. And let's also define the verby version of this word. It's an archaic term, to complect. But let's use it anyway. I mean, to complexify. Let's use to complex, it's a better word. As an opposite to simplify. Just because it's a useful word to put in our heads to understand this. It's nice to have a verb for it as well. So what we're looking for is this space between all of the parts of our code, this interaction space. The more interactions we have, and the more woven these interactions are, the more complex our code is. That's what code quality metrics want to limit. The thing is, creating code is creating these connections. There is a minimum amount of these connections that have to be created. Because if we don't have these interactions, our software doesn't do anything. We can't just put a bucket of code Legos and throw them out over the floor and say it's done. That's not how it works. Everything we do in software is creating these connections. The thing is, once we do make these connections, unlike Legos, it is quite hard to get these things to disconnect. Once we've put the connection there, it requires more than double the effort to get it away. Because we first need to deprogram the connection, we need to re-implement the feature in such a way that the connection isn't there, and then we can get to working on the thing that we actually wanted to work on. So these bad connections, if they ever show up, are going to be a big problem. And that's what code quality is about, eliminating as many as possible of these bad connections. Connections that don't need to be there, but we put in there by accident. Chances are you've heard of this terminology before. Inherent complexity and accidental complexity. That's what code quality is about, minimizing the amount of accidental complexity. And we minimize this amount in order to allow for the inherent complexity that must be there, that we can't get rid of. Okay, cool. Well then why do accidents happen? Why do we get accidental complexity? Why does it show up? Well, here are my theories. There's this essay, or this part of a larger essay, a chapter called Worse is Better. The claim there is that getting halfway, but getting there first, will create a small virus that has better survival characteristics than taking your time to do the right thing. Because taking your time to do the right thing will get you nothing for a long time and then suddenly get the right thing. Getting halfway there and getting your users infected, and your users are probably you in a future version of yourself. Getting yourself infected by something that kind of works has a chance of getting you locked into doing the worst thing. And then eventually you bring that up from halfway to 90%, but you'll never get to 100%. Then there's a not invented here syndrome. This one means, well, if it's not invented here, it's not good enough, so we need to make it ourselves. So there was a lot of duplicated effort, and people got allergic to duplicated effort, and now we have an aversion to creating things ourselves, even though sometimes it is correct to make things ourselves. But we're too scared to try. Then we have the move fast and break things way of thinking. It is easy to get started with a framework. It is easy to take existing code and start using it. The chances are, though, that this existing code possesses complexions, introduces complexity that we don't need. It makes connections that we didn't really need and we absolutely don't want. But they're there, and we get a lot of initial velocity for starting with something instead of starting with nothing. And then finally, just a bit of tradition. We built a foundation that made some connections that didn't need to be there, and then we were too busy building to actually look at this foundation. An example of this would be object-oriented programming. All right, so let's look at how do we avoid accidents. First step, avoid easy. Seriously, if something is readily available, something is right there, it is easy to use, you already know how to use it, it's a tool you're familiar with, it's a framework you're familiar with, that doesn't mean it's a good choice. It doesn't mean it's the right choice. In order to find what the right choice is, there's no avoiding this. You have to think slow and you have to think long term. And while you are thinking slow, try to choose simple things. Don't choose things that have complexity built into them. Here's a list. Instead of making stateful things, try to get the state out of there. Just use raw values and raw data. If your values don't need to depend on time, cool, get it out of there. Instead of using methods to objects or methods to functions, then modify hidden state in the background, just use pure functions. Don't have side effects in your functions. That way they won't modify states and they won't be time dependent. Instead of using references to other modules and other objects, use queues and channels. That was the diagram I went through at the end of the interacting state machines patterns. You have all these unused potential interactions to methods that you don't really need access to, but you get access to. These potential interactions are things that you want to get rid of. And you also, with references, have these uncertain ownership semantics where everybody communicates with everybody and everybody modifies everybody, but nobody really does anything because the thing that does something is main. Objects, of course, combine all of the above and all of the problems with all of the above, so don't use them. Inheritance, it complects types. It takes one type and combines it with a supertype. Why would you do this? I don't know. Use templates. Instead of using conditions, conditionals tie the structure of the order of the conditions with the behavior of your code. If you modify the else's in your if to one goes before the other, or the other goes before the one, then it might change the behavior of a program. This isn't, rule sets aren't, or table-based methods aren't always properly supported in programming languages, but if you do have a way to express your logic in a table-based format, go for it. This way of choosing simple things, this is the foundation that I used in part 1 of this lecture series. This is why we do state machines. This is why we do interactions with queues and channels. Now, since everything about code quality seems to be about interactions between things, the complexity of these interactions, chances are we can think of these interactions visually and geometrically, because they are interacting with things that the code that is written on the page. And the way we look at the code is important because that's what we do with code. When we're both reading it and writing it, we're also looking at it. Here's my claim or hypothesis or work in progress for ways of actually thinking about code quality with a visual metaphor in terms of geometry. I hope this is useful. It's at least more concrete than just say, limit the amount of accidental interactions in your code. Let's see if we can find these accidental interactions by visual metaphor. I have not talked about error handling this year, but I will briefly talk about it now. You're all familiar with how to do exceptions. You may not be familiar with scope guards, which are available in C++, D, to some lesser extent Go. These two pieces of code do the same thing. Look at the geometry of the code. The left one, of course, has an extra indentation. The A's and the B's are separated by different amounts. The A's are far apart from each other. Do A and undo A are far apart. Do B and undo B are close together. They're also at different levels of nesting. The forward flow of doing A and the backward flow, or the forward flow of doing things and the backward flow of undoing things, well, forward goes in and backwards goes out. But on the right-hand side example, forward goes forward and backwards goes upward. The geometry of the right-hand side is simpler. Here's an elevator project from a previous year. I don't remember what year it is. That text size might be a bit small for the people in the room. This is the event manager. It is the hub, the spider in the middle of the web. I'm just going to highlight a couple of variables that have instances in multiple places. The three variables in green is a lift map, which is the state of each individual elevator that we know about, including what orders it has. Yellow is the door timer, which is the timer used for closing the door. In blue is a stuck timer, which is a timer used to notice that we have stopped moving and we are stuck between floors. Now the question is, how did this happen? Well, imagine drawing a complete graph between all of the blue nodes, and then drawing another complete graph between all of the yellow nodes, and then drawing another complete graph between all of the green nodes. And you'll see you'll have one heck of a web. The reason this happened is because this module is the only module in the program. So, for example, case lost peer IP, which is roughly in the middle. When we lose a peer, the thing that handles the loss of a peer needs the door timer and the stuck timer. And the question is why? Well, if we lose a peer, we might need to take over its order. And when we take over its order, we might start moving, in which case we need the stuck timer. Or we might need to close the door, or open the door rather. In that case, we need the door timer. This wouldn't happen if the state machine for executing orders was a separate module. We wouldn't need to bucket brigade these channels. So having fewer things does not mean that it is less complex. It just shifts the necessary complexity to somewhere else. In this case, all of the complexity has been put in this giant web. So let's see if we can get some nice guidelines out of this one. Don't weave your channels. Don't pass your channels around more than absolutely strictly necessary. The channels are points of complecting. The channels are the things that weaves your program together. Use them as few places as possible. Read them once and only once, and that should be in your for select. Write to them once per case in this for select, at most. No more. The channels, since they interact with other modules, present this unknown potential. What happens when I write to this channel? Well, it goes somewhere else and I don't want to need to be concerned about it. So if you pass them around, well, you're passing this unknown interaction around as well. Don't do that. As an extra little bonus, keep these functions pure. This is in a for select, and instead of putting the code that does something directly in the for select, they decided to hide everything under the carpet and create a single function for each. Of course, when every function has somewhere between 4 and 7 parameters, your carpet is going to start getting a bit of a bulge. So just be honest, if you're doing modifications, put it directly in the for select. No need to hide stuff in functions that are only single use. Here's another tiny section of a elevator project. There should be one more. Yeah, there we go. We have this orders info, orders to be cleared, old orders, and unconfirmed orders. And this clear order info is a data type that contains a table of orders, and the map string is then for each elevator a table of orders. So in this case we have for each elevator a table of orders to be cleared, for each elevator a table of orders that are old, a table of unconfirmed orders, and for each elevator some orders and info. I would hope there is info in the orders and the info isn't separated, so it needs to be anded in there, but hey, here we are. There's too much data here. We can simplify this by reducing the amount of data. So instead of having multiple variables of the same type but with different name and different usage pattern, maybe we could have one variable with multiple usage patterns. So instead of having just the table of booleans, it's a table of something other than boolean. It's a table of, is it confirmed, is it old, is there no order, and so on. That would get rid of these extra variables, because it can't be both old and unconfirmed and new at the same time. That doesn't make sense. It needs to be one of these. So instead of having table of booleans, have table of something more informative than boolean. That would get rid of these extra variables. Here's from exam 2019. Okay, it doesn't show up both at the same time. It's from exam 2019. Again, small text for the people in the room, but you might be able to see visually some repetition here. There's a single if in some of these, or the top left one has a single if, and then nested within that there is some amount of statement for order timestamp, and then there is this other thing with if direction store orders to file or send order broadcasted on the network. The names of the functions are flag order as accomplished, flag order as taken, flag order as marked, flag order as calculated. But in all of these there is this extra little flip at the end with an if. If it's a cab call, put it in the file, otherwise put it on the network. For each of these. The exam question was suggest improvements. Well, let's suggest some improvements. But first, let's just look at some other problems. There are some hard dependencies here on stateful things. There's both network disk and also elevator hardware in here. So all of these functions are pretty damn stateful. And none of these functions actually do anything. They're all functions that need to be called, and it's the responsibility of the caller to call them in the right order and at the right time. So these are also just like carpet functions that don't do anything other than make a bad attempt at hiding the dirt. Well, let's get to the meat of the problem. There's some repetition here, and this kind of repetition is a hint that there's something that we can factor out. Now the question is, of course, what is this something that we can factor out? Well, we're going to have to look at it closer to see exactly what this one is, but here's the correct answer. This module tries to do several things. It tries to both perform the assignment of the orders and the reassignment of the orders, and it also performs the distribution as well as saving, both to the network and to the disk. You can think of these as the same thing. Distributing to disk or distributing to other nodes is the same kind of thing. This module is not one module. It is at least two modules. Again, same as before. You get extra complexity by keeping things in one place. Having less of something doesn't mean it's less complex. Here's this year's trial exam from just last week. A function called delete flag, which is chances are that this is the function that is called when an elevator arrives at the floor and is supposed to remove the elevators and clear the flags and set the lights to 0. And the question is, how the fuck did this happen? Now I can tell you exactly why this happened. But first, let's look at the geometry. Let's highlight highlight the conditionals here. These are the things we are conditioning on. Look at the green things. Nice Boolean functions. I like them. Let's keep this. This is good stuff. The orange things for floors, well, we have 5 cases for checking floors. We have is top floor, is bottom floor, else, and then we also have an extra one for not top floor or not bottom floor. The geometry here suggests that there is room for simplification, quite trivially. And then we have this direction up and direction down while we're double checking them. And one of these times we're also reading it directly from hardware, and one of them we're reading it from the parameter list. I think this is just straight up a mistake. I'm assuming these are supposed to be the same thing, because anything else wouldn't make any sense. Again, the geometry here suggests that since one of them is inside an else and an extra if, and the other one is in the outer ifs at the bottom, suggests room for simplification. Now, honestly, I did remake this one just to see what happened and why this happened. And in the process of remaking it, I discovered that I had in fact written this code before, but pinky promise, I did write this one from scratch. This is the same function. Now notice that the orange one for checking for floors is gone, and checking for direction is at a single level in a single place. At one level of nesting, I mean. And this code does the same thing. However, there is a bug. I forgot at the top, right before the switch, I forgot to actually clear the button lamp for the button command. Don't tell anyone. But it should be, again, from the geometry, fairly obvious that this is a problem, because in every other case there is both a flag table modification and a button lamp modification. But at the single one at the top there is only a flag table modification. So it should be reasonably easy to find and fix this bug, just from the geometry. Now the question is, how was I able to make this fix? Well, let's look at that. This repeated kind of double checking, if you get this, it can probably be straightened out. And when we have these kinds of convoluted conditionals, it's probably the result of a bad data structure, which was the case here. The data structure was bad. So I changed the data structure. That's how I got the simplification. Their data structure was a 4x2 matrix of floor times up and down. They didn't have the internal buttons stored. They stored the internal buttons by proxy by saying if it's an internal button, it is equivalent to both up and down at the same time. That's how they ended up with this messy logic. I said, fuck that. I don't need to save 4 bits of memory. I have 4 bits of memory. I'm going to use them. So I changed it to a 4x3 matrix for each floor times up, down, and stop. And that let me simplify the code. They complected up and down to create a proxy for the command or the inside button direction, or the stop direction if you want to. I also, in what I would prefer to be my version, if I were to do this absolutely properly, I would have both a direction, up, down, and stop, and the button type, up, down, and command, as separate types. Because they don't need to be associated. They are conceptually 2 different things. And talking about the stop button in this situation doesn't make a lot of sense, and talking about the command direction doesn't make a lot of sense either. So I would have preferred if these were separated, but let's not for now. Also, side effects. These functions are highly stateful. They modify the hardware. They modify a table that is outside of scope. At some point you're going to have to write to the hardware and write to the table outside of scope, so I'm not going to knock them too much for this. It's fine, you have to do it at some place, and there's the algorithm for doing it. Well, let's look at it. Is it really that complicated? No. Can you make it complicated? Yes. But if you do it properly, I don't mind this statefulness with 2 levels of nesting, it's fine. I hope this geometric way of thinking about code quality is useful, and I hope thinking of code quality as a property of something that lies between the lines and not on the lines is also useful. It is definitely a different way of thinking about code quality, and it also completely removes you from this checklist. But I do encourage you now to go back to the checklists with this new understanding to see if you can find the necessary context to make all of these points make sense, because they will make more sense in the context of minimizing accidental complexity. With that way of thinking, the checklists now make sense. Cool.
No, the Code Complete book, it's a good book still. It's more than its checklists. There is arguments there that say we have examined IBM's bug database over the last 50 years and found that the procedures with less than 7 parameters have in fact less bugs per line than procedures with more than 7. There is a breaking point there. Therefore, 7 sounds like a rule. This is discussed. Of course, there are a top-down intuition that Anders promotes here that lies in what he examines to start with. What kind of rule does he want to construct? What analysis of the bug database in IBM, this Connor, what's his name? Which analysis he does from the bug database, of course. But then the arguments, there are a lot to learn. It's nice to know that if you are to put words to why the ordering of the if and else parts, what is the better one? It's nice to have seen the argumentation from the, in fact, chapter, and not only the checklists of Code Complete. Just so.